The main purpose of this example is to demonstrate the results of statistical error analysis with uncorrelated thickness errors of individual coding layers. In the file, Project menu of OptiLayer, open the directory LEC25D16. Load into RAM the data files needed to run this exercise. These are the substrate glass N equals 1.52, the layer materials N equals 2.35, and N equals 1.46. In the design database, select the file SWP-21 by quasi-Newton and load it. Open the T and R and phase option in the analysis menu to see the transmittance of this shortwave pass filter in the 400 to 700 nanometer spectral range. In the analysis menu, select Error Analysis option. In the Error Analysis Setup window, use Characteristic tab to set the Analyze Spectral Characteristic and Statistical Analysis parameters. By default, the calculation of mathematical expectation, M, and quarter of deviations, D, is enabled. This means that at the end of the statistical analysis, the results of individual error tests will be replaced by these statistical characteristics. Use Thickness tab to set levels of errors in layer thicknesses. Recall that in this option, we consider uncorrelated thickness errors of individual layers. It is possible to consider two types of such errors, which are called additive and relative thickness errors. The level of errors of the first type does not depend on the layer thickness, and the level of errors of the second type is proportional to the layer thickness. We assume that in both cases, the mathematical expectations of errors are equal to 0. In this case, the level of errors is determined by the standard deviation sigma of the normal distribution. Randomly generated errors will be within the corridor from negative sigma to positive sigma with a probability of 68.2%. The standard deviation is called the level of thickness errors. In the case of additive thickness errors, we set the level of thickness errors directly in nanometers, layer errors ABS field. In the case of relative errors, their level is set as a percentage of the thicknesses of the respective layers, layer errors rel field. For example, a relative error of means that the standard deviation 1% is 2 nanometers for a 200 nanometer layer and 0.5 nanometers for a 50 nanometer layer. Error levels can be the same for all coding layers, coding tab, the same for layers of a given material, material tab, or set individually for each coding layer, thickness tab. Let us set 1% relative errors for all coding layers. Click the Run button to start error analysis. Because the calculations are fast and plotting a large number of individual error test results can cause confusion on the screen, you will see the final statistical characteristics of MX span D. To view the results of individual error tests, you can specify a pause after each plot in seconds. A notable result of the performed analysis is the insignificant influence of layer thickness errors on the spectral characteristic of the filter in the high reflection region. There is a general theoretical result stating that errors in layer thicknesses cause only small changes in the spectral characteristics of optical coatings in regions of high reflectance compared to other regions. To run the second example, load the design 66 layer 4 cavity NBF at 600 nanometers. In the T and R and phase window, set the wavelength range to 585 to 615 nanometers. You will see the transmittance of a narrow bandpass filter with a central wavelength of 600 nanometers and a 50% pass bandwidth of about 4 nanometers. The filter has steep transmittance slopes, which is due to its special structure. This is a 4-cavity filter that can be seen using the refractive index profile window. Let us run the error analysis with the same parameters as before, that is, with 1% relative errors for all coding layers. Click the Run button to start error analysis. The statistical characteristics of M, X, B, and D show that at this level of errors, the spectral properties of the filter are completely destroyed. Reduce the relative error level from 1% to 0.1%. Set the number of tests to 20 and the pause after each plot to 1 second. Run the error analysis mode again. The results of individual error tests are still completely unsatisfactory. Note that the relative error level of 0.1% corresponds to additive error levels for most layer thicknesses of about 0.1 nanometers or less. It is therefore obvious that multi-cavity filters of the type in question cannot be manufactured using time or quartz crystal monitoring. The only way to successfully manufacture such filters is to use turning point optical monitoring, which provides self-compensation for thickness errors in different coating layers.